Hey, physicists, welcome to week 2 of our continuous learning, and hope that you guys are doing well. Just for clarification, in case things are confusing, last week we asked you to watch the videos with the new information and then do the activity. But for this week's content, I think that it makes the most sense for you to do the activities first. So if you haven't yet done that, go ahead and go back onto Canvas and take a look at the PhET simulations for gravity and electricity. Work through those. There is a key posted there as well. So go ahead and work through those first and then come back and watch this video. So glad to have you back. Hope that the PhET simulation made sense to you and started to kind of get your brain moving towards understanding how gravity and electricity both work. So we spent the beginning of our time together this year talking about forces, and we're going back to the forces now, to two fundamental forces that make up our universe. There are 4 of them in total. We're just going to focus on these 2. So this sheet is also available on Canvas. I would encourage you to print it out just to help you stay engaged with the notes, but there's no requirement for that. That's all up to you. So do what you need to do. If you need to pause, feel free to do that, and then come on back when you're ready. Okay, so we're going to take a look at these 2 forces. We're going to go ahead and just work on the column for gravity first, and then we'll come back to electricity and kind of see how they're related. But even before we do that, I want to come back to the word force. We talked about it a lot early in the year. I want to make sure that you're feeling comfortable with what a force is. Hopefully, every time you hear the word force, and I know it's a little bit confusing given that we had Star Wars Day earlier this week, so don't get too overwhelmed by that, right? We're not talking about the connection that Luke and Leia have or that Kylo and Rey have. We're talking about a force in terms of physics. The forces that we're talking about are interactions between 2 objects. And the key here is that any of these interactions that we're talking about are always between just 2 objects. Okay, the interactions might be different depending on the type of force it is, but it's always an interaction between 2 objects. For example, when we're talking about gravity, the force of gravity exists between any 2 objects with mass. And you may be saying to yourself, well, what objects or what things don't have mass? And that's a conversation for another time. In the big picture, the one thing I'll throw out there just to kind of whet your appetite in this case is that light, we usually talk about light as a wave, as we have been doing for the last few weeks, but light as a particle is an object with no mass. So just let that kind of sit there. Go look it up later if you want. But anyway, all of the objects we're talking about with gravity are objects with mass. Okay. Now, you found out when you were using the PhET simulation that the gravitational force depends on a couple of different things. One of them is mass, which makes sense given that gravity is a force between any 2 objects with mass. And remember, we said that there are 2 of them, so we're going to call them M1 and M2. Okay. Hopefully you found as you interacted with that simulation that as the mass of object 1 or the mass of object 2 goes up, you saw that the force of gravity interacting between the 2 objects also increased. Okay, and we'll come back and we're going to fill one more thing into that box in just a minute, but for right now we'll leave it right there. You hopefully also realized that mass was not the only thing that the gravitational force is dependent on. It also depends on the distance between the 2 objects. And generally, we talk about that distance as a radius. So one of the reasons is because often when we're talking about gravitational pull, especially in an astronomical context, we will talk about it as, the orbit or the radius. But in general, when we're talking about that distance, we're going to mark it with a letter R. And I'm guessing if you were working through that simulation that you found that as the radius or the distance between the 2 objects got bigger, instead of the force getting bigger, that would be weird in this case, the force of gravity actually gets smaller. So the distance between those two objects, as it goes up, the force goes down. Okay, so that's where we're going to leave those for right now. And again, we'll fill some more stuff in there in a little bit. But the other thing that I want to do now is to come way down. We're actually going to skip this next thing that says direction of force and come down. Oops, even further than that. Sorry, I got excited. Let me go. Come all the way down to the equation for the force. Because at the end of your simulation, at least the part about gravitation, we had asked you to develop a proportionality or a relationship between those two objects. And so I wanted to go ahead and write that in here. We're going to write down the equation as well, but I want to write the proportionality down first. So the force of gravity is dependent, we said, on two different things. It depends on mass and it depends on the distance. I'm actually going to jump back up here. Sorry, I got a little ahead of myself. The force is proportional to the mass, right? As one goes up, the other goes up. So proportionality just means that you could put a constant in there and everything else would work out. So as mass goes up, gravity goes up. And that's actually true for both masses. So here I'm going to say that the gravitational force is proportional to both mass 1 and mass 2. Either one could increase or both of them could increase, and either way, that's going to increase. The radius, though, actually causes the force of gravity to go down. So this gets a little bit funny, and the simulation as it's written is a little bit hard to figure out exactly what this relationship is, which is why we're doing this video as well. Okay, so as one goes up, the other goes down. So we know that it's going to be some sort of inverse. So it's going to be 1 over r, but it actually turns out that it's not just 1 over r. If you go in and actually take data for this, and you may have been able to see it in the work that you did, that it's not linear, it's not a direct inverse proportion. It's actually proportional to 1 over r squared. This may have been something that you had an inkling about when you were doing your simulation, but it totally may not have, and that's okay too. No worries, no stress any way in that sense. I just wanted to make sure that you know that you see that, and indeed that this actually goes here. So this is r squared. So this is what you hopefully perhaps may have ended up with from your simulation. What we're going to go through now, though, is to figure out that proportionality constant and figure out what that's all about. So in order to have a proportionality constant, basically what we're doing is we're going from a proportion to an equal sign. So we're going to say FG is now equal to, well, there's got to be something in here that makes these two things equal. That's the proportionality constant. So I'm going to just leave a little box there. M1, M2 over R squared. And that thing that's in there, we decided, not Mrs. Murphy and I, but the physics community as a whole, when they were developing this stuff, decided that we're going to call this proportionality constant big G. And that proportionality constant is called, wait for it, pretty exciting name here, the universal gravitational constant. That's a pretty big deal. And to be very, very clear, big G is not the same as little g. The little g that we've been using for much of the year, right, 9.81 meters per second squared downward, that is true at the surface of the Earth at sea level. Okay, if you go up to Mount Everest, you go down to Death Valley, that value changes. If you go to the moon, that value for sure changes. This thing right here is a universal gravitational constant. That means anywhere in the universe, this value is the same, okay? And this constant is equal to, now this is kind of a weird number, don't have to memorize it, but I'm just letting you know what it is, 6.67 times 10 to the negative 11th. Huh? Yeah, it's kind of a weird number. Now, just a little fun fact for you today. You've heard of Isaac Newton. We've talked about him. You know that he's not my favorite person in the world. Well, he's given credit a lot of times for, quote, discovering gravity. So number one, he didn't discover it. That would imply that it didn't exist before. Definitely Rocks have been falling towards the earth. Apples have been falling from trees for long before Isaac Newton. Isaac Newton did, though, develop the idea of universal gravitation, but this is as far as he got. It took him another 100 years. It took scientists another 100
Here's what I
years.
found.
Oh, Siri thinks she found it too. Sorry about that. It took them,
I'm sorry.
oh my gosh, 100 years to figure out what the value of that was, that 6.67 times 10 to the negative 11, which is just, fun fact. Isaac Newton didn't know everything. That's always good to remember. Not anybody knows everything. Hey, what are the units of this thing? Well, we can figure that out. If we look at the units of what we know so far, the force, well, forces are always measured in newtons, right? This unknown thing, I'm just going to put a box here and put a question mark. Maybe I've been watching too much Mario, I don't know. My masses are measured in kilograms, so this is going to be kilograms times kilograms, or you could say, hey, that's kilograms squared. You're right, it is, divided by meters squared. So we can use this, we can solve for the unknown box to figure out what that is. So I'm just going to go ahead and put question mark box. Well, that's going to be newtons meters squared per kilogram squared. So the units of this weird constant, not only is it a weird number, it's a weird unit as well. So it's 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Okay. Again, you don't have to have that memorized. It's on your sheet. You'll always be given it if you need it, but it's just nice to kind of know where it's from. All right. The very last thing that we need to do on this side of the chart is to talk about the direction of the force. So hopefully you noticed when you were doing your interaction PhET simulation, hopefully you noticed that those arrows never change directions when you were talking about gravity. In fact, gravity is always an attractive force. It always, always pulls objects together. So any two objects that have mass will have an attractive gravitational force between them. Might not be very big, but it is always there. Okay, so there's gravity. We're halfway there. Electricity, let's take a look at this one. So again, you did the PhET simulation for gravity. Now we're going to do the PhET simulation for electricity. So we have to have two objects again, but in this case, instead of the object's mass being the thing we care about, the thing we care about here is that we have to have objects with an electric charge. So hopefully you remember the idea of positive and negative charges. That was, I'm sure, drilled into your heads when you guys were in chem, but we just want to make sure that you remember that those are the two fundamental types of charge, right? You've got positive, and I usually write that as parentheses plus, and negative is parentheses minus, okay? And just for reference, so that you have it here in case you need it, and again, I think this is on your equation sheet, a couple of fundamental and simple charged or values of charge. An electron, I write that as E negative, has a charge Q sub E. Friends, I do not know why it's Q, but it is. That's what we use for charge, is Q. Of negative, right, because it's an electron. Electrons have a negative charge, 1.6 times 10 to the negative 19th coulombs. Another weird word, but it's just a capital C. That's the unit, the SI unit for charge. So an electron has a charge of negative 1.6 times 10 to the negative 19th coulombs. A proton, so I'm going to write that as P plus, has a charge. Well, it actually is exactly the same magnitude, right? We know that an electron and a proton have the same magnitude of charge. One's just positive and the other is negative. So the charge of a proton is 1.6 times 10 to the negative 19th coulombs as well. The reason I point this out is because I don't want you to get confused. The negative that we care about is the one right here. The negative that's in the exponent is just telling you how big that charge is. And the size of the charge in both cases is exactly the same, okay? So the charge of an electron and the charge of a proton, the magnitudes are the same. The exponents are the same because they both have a very, very small amount of charge in terms of coulombs. Okay. All right, so let's keep cruising here. Hopefully, as you were going through the simulations for electricity, you noticed that there were a lot of similarities to the simulation for gravity, and that was on purpose. There's a reason that we teach these two together, okay? So the force for electricity depends on the charge, right? And we just mentioned that the charge is marked with a Q. There are two objects because a force exists between any two objects, so Q1 and Q2. Something important to note is that while gravity acts on objects with mass, and like I said, that's pretty much everything that we know about, except for light, um, electricity only acts on objects with electric charge. So you think about those atomic particles that you know and love. You've got the electron, you've got the proton, you've got the neutron. Electricity, or the electric force that we're talking about, only interacts or only exists between charged particles. So electron, 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 proton, 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 but not anything with the neutron, okay? Because the neutron is neutral. So that's just one of those little things that I want to make sure that you are aware of, okay? So we know that as the charge on a particle or on an object increases, hopefully you found that the force also goes up. And then similar to what you saw with gravity, as the distance between the two charged particles goes up, and again, we're going to write that as r, as a radius, okay? That's, again, it doesn't have to be a circle, but we just always call it r. As the radius increases, the force, the electric force goes down. So that's a pretty important deal. And, well, here we're going to go ahead and jump down. Well, no, sorry, I'm not going to get ahead of myself this time. Hopefully when you were doing the proportionalities and you played with those values to make one double and find out what happened to the force and that sort of thing for Fe, you found out that the force was indeed proportional to the charge. And that is true for Q1 or Q2, doesn't matter which one. And that the electrostatic force is proportional, well, it's inverse, right? We've got one that goes up and one that goes down. So it's 1 over r, but not only is it 1 over r, the math works out, the measurements work out, all of it works out, you guys, to say that it's 1 over r squared. This right here is a big old deal, right here, bam, okay? In both of these cases, both for gravitational force and for electrostatic force, they are both what we call inverse square laws. And I'm going to write that down just because it's a nice word to write down, or a nice phrase. Inverse means as one goes up, the other goes down. Square, and it's because indeed it's not just the inverse, but it's the inverse square. And this is one of the things that makes physicists really, really happy, to have such nice parallelism between two things that seem so very different. So it's kind of an interesting observation to make. All right, we're going to jump down here to the equation for the force. Let's observe again. So given the proportionalities that we set up here for Fe as it relates to the charge and the distance, we can say Fe is proportional to Q1 and Q2 and is inversely proportional to the square of the radius. All right, so now we can do the same kind of game that we did before. We can say Fe is equal to some mystery thing that we don't know yet, right? Because that's what a proportionality is. It's just something, a relationship where there's a constant. That's the constant we're looking for. Q1, Q2 over r squared. What is that mystery proportionality constant? Well, in this case, it is named after a physicist named Coulomb, Coulomb. This is Coulomb's constant. I do not know a lot of detail about Coulomb, but I do know that he got a lot of stuff named after him when it comes to electrostatics. For example, the Coulomb is the unit, and we've got Coulomb's constant, and actually, secret, this is really Coulomb's law right here as well. So Coulomb's constant, just sorry, that was a little bit of an aside, is marked with the letter K and has a value. Again, they found this experimentally, right? You know these two things are related. How are they related? What is the constant? It is 8.99 times 10 to the ninth. And then so we're going to write our K down in here, and then we're going to figure out our units, do very similar work to what we did earlier, but let's go ahead and do it. So we've got newtons for our force is equal to our mystery box times, well, we've got Q times Q. So that's Coulomb times Coulomb divided by meters squared. We can solve for that question mark box. And we see that we've got Newton meters squared per Coulomb squared. Okay, so those are going to be our funky units for this constant. So we've got Newton meters squared per Coulomb squared. Again, you don't need to worry about those units. You don't need to have that memorized. Just know that that's there. One other little thing that I want to point out here, because we love all this nice symmetry and also things that are very, very different. When we look at these two constants, I want you to notice how very different they are. The universal gravitational constant has an exponent of 10 to the negative 11th. That means that it's very, very, very small, right? So it's, if I move my decimal point over, I have to move it to the left 11 spaces. Okay, so it's going to be a very, very small number, whereas Coulomb's constant has a positive exponent, right? That means you're going to move the decimal to the right 9 spaces. That's a very, very big difference. And that difference is going to come into play. So just wanted to make sure you saw that. All right, the last thing that we've got for this chart is to talk about the direction of force. And this should not be a surprise. You guys have been doing this for a long time. You've been doing this in your classes, science for quite a while. So the game is that unlike gravity, where the force is always attractive, in electricity, it depends on the signs of the charges. So it can be attractive, okay? And it's attractive if you have opposite signs. What do I mean by that? I mean that you have one of your charged particles that has a positive charge and the other one that has a negative charge. Okay, so if you have a positive and a negative, then those two objects are going to attract. On the other hand, it can also be repulsive. Okay, and that is true when you have like charge or like signs. So that would be a positive and a positive, or of course, a negative and a negative. Okay, in either of those cases, it will be repulsive. One other just little side note, because it's kind of a pet peeve of mine, and that is to say that when we're talking about charges, charges are positive and negative, okay? They are not the same as magnetic poles. So we are not talking about north and south. This is one of those things that if we had had more time, if we got to hang out together this spring, we totally would have gone over, would have gotten to do some magnetism as well, but it was kind of one of the things that had to shake out. But I want to make sure that you're aware of that charges are marked as positives and negatives. Magnet poles are called north and south, but they're not quite the same thing. Okay, so that is all for this chart. There are some problems on the next page, and I'm going to record a separate video for you for those. And I would strongly encourage you to take a look at that before you work on the assessment. Thanks so much for watching. Have a great day.